everybody, this is Mr. Peterson coming to you from the Peterson Kitchen. You probably thought Vesper was just a Druish princess, but she's not. You probably don't even know that joke because you don't watch good movies anymore, but this is a picture from the movie Spaceballs, which is a funny movie, but not appropriate for school. And this princess right here, that's Princess Vesper. And today what I'm here to talk to you about is what's called Vesper theory. And Vesper stands for Valence Shell Electron Pair Repulsion Theory. It doesn't actually have anything to do with Druidia or Jewish princesses or Spaceballs. In fact, we're going to use an orange, some marshmallows, and some pieces of linguine in order to learn, in order for me to get you started and everything that you need to know to be dangerous with valence shell electron pair repulsion theory. So this simulation is the simulation that you're going to use in our lab this week, and it is a fantastic tool that's been just a couple of years that this has been around for helping people to learn this. What used to be kind of tough to visualize and see, this is a really good tool for. So what you got to imagine is that this is the middle atom in a molecule that you have drawn, okay? And around this middle atom are going to be groups of electrons. The groups of electrons are either going to be a lone pair of electrons, or maybe a single bond of electrons connected to another atom, maybe a double bond or a triple bond, okay? All of those things, as far as Vesper is concerned, this theory, count as one group of electrons. Let me rename them again. There's four things. A lone pair is one group of electrons. A single bond is one group of electrons. A double bond is just one group of electrons, or a triple bond is one group of electrons, okay? So let's imagine that this is that middle atom and that it has got two groups of electrons around it. So the, Alexa thought that I said her name.
Another Amazon customer. Company's profile page for Imaginext Group, including stock price.
The first group of, in fact, I'm going to break this piece of linguine into two pieces. So suppose that I have got a group of electrons right there, okay? What valence shell electron pair repulsion theory tells us is that different groups of electrons want to be as far from each other as possible. So if we have a group of electrons here on one side of the atom, and they want to be as far from each other as possible, then we have a second group of electrons, where are they going to go? Well, it stands to reason that they would be on the opposite side of that atom, and so they would line up straight across from each other. We would call this arrangement of electrons we'd call the geometry is linear. Okay, so I'm going to remove all these. So if we had two groups of electrons around a middle atom, they're going to line up and be on exactly the opposite side from each other. We call this electron geometry linear. Okay, now what if we had three groups of electrons? What if there was three groups? Like, again, they could be single bonds, double bonds, triple bonds, or lone pairs. Any of those things counts as one group. How would three groups spread themselves out around that middle atom so they could be as far apart from each other as possible? Well, it turns out that they would spread themselves out so that they were about 120 degrees separated from each other. That's how they get as far from each other as possible. So this is flat. They all line up on the same plane this way. They're all flat right there, but it's kind of split up. There's 120 degrees between those groups of electrons. We call this trigonal planar. Triangle plane. Triangle plane. Trigonal planar. So we'll see here if I add a third group of electrons, the electron geometry is trigonal planar, and you can see it there. They are 120 degrees from each other, and it is planar. Okay? All right, so now we're going for the killer question here. What if we go to four groups of electrons? You would be a very normal chemistry student if you thought to yourself that linguine is too fragile to do this. If you thought to yourself that four groups of electrons should spread themselves out and look like a cross or like a T, okay? We would call this arrangement square planar. Okay, but you, just like most other normal chemistry students, would be wrong. if we take advantage of the fact that we have got three, if this had to be a flat molecule, then you're right. This is how they'd arrange themselves. But it doesn't have to be a flat molecule. 4 groups of electrons can arrange themselves further apart than that. That would have been 90 degrees apart. They can get themselves 109.5 degrees apart from each other by assuming an arrangement that we call tetrahedral. Okay, why tetrahedral? Well, tetra means 4, right? Hedron, like a polyhedron or like a dodecahedron. When we say hedron, we're talking about 3-dimensional shapes. If you were to wrap this bad boy up and give it to somebody as a Christmas present, it would be a 4-sided Christmas present. I bet you've never gotten a 4-sided Christmas present before in your whole life. So, I mean, what an excellent idea to give to somebody for their birthday. You make them a tetrahedron, you wrap it up, and voila, it's my birthday next week, I'm hoping. So, in any case, if we added a 4th group of electrons here, there's a better look at kind of what the shape is. They are a little further than 90 degrees apart from each other. So that square planar shape is not the way that 4 groups of electrons will work themselves out, because they can get further apart by doing a tetrahedral, 109.5 degrees apart from each other. Okay. It turns out if we keep on going with 5 groups of electrons, that we would come to a shape that we call Trigonal Bi-Pyramidal. Okay, Trigonal Bi-Pyramidal is this, like, so there's like a north pole. Let's see here, what do I got? I got the north pole there is up the top, south pole right there, and then like around the equator, they're 120, oh boy, this is tough to show. Around the equator, they're 120 degrees separate from each other. There we go. There we go. Okay, so you're looking at like down on the north pole, the south pole's going away from you, and you can see around the equator, it's like that trigonal planar shape that we had before, but with one poking up out of the top and the one not poking up out of the bottom. That's Trigonal Bi-Pyramidal, and if we added another one, a 6th one, we call this octahedral, and this is just 90 degrees separated from each other all the way around. Okay, now. This electron geometry is always a function of how many groups are attached to the middle atom. When you got 2, it's going to be linear. When you got 3, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. And 6 is going to be octahedral. That is always going to be true about electron geometry. What we're going to find, though, is that the molecule's geometry, which is like the molecule shape, can vary. And it can be different. It can be the same as the electron's geometry, or it can be different than the electron's geometry. Let's have a look at our tetrahedral molecule that I've got here. I also happen to, now we hide, fortunately, we hide marshmallows from my children, so otherwise they would break into the pantry and eat them all the time. And we hid a bag of marshmallows. We're not really sure how long ago, but they're still, you know, actually fairly soft here. So we're going to use these marshmallows as other atoms. If we had 4 groups of electrons around the middle atom, they're going to arrange themselves tetrahedrally. Okay? Now, if only one of them is actually attached to another molecule, the molecule shape is actually, we only are looking at what the atoms are doing. We ignore these other lone pairs of electrons. So if there's only 2 atoms in a molecule, guaranteed every 2-atom molecule has to be linear. There's only one shape that a molecule with 2 atoms can be. It's linear. 2 points define a line. And so if we've got one atom and another atom, the shape between them is going to be linear. Okay? If all 4 of the bonds had something attached to them, like let's say that we had 4 groups of electrons around the middle atom, so we have this tetrahedral arrangement of bonds. Okay? They're all attached to somebody. Then the molecule shape is also going to be tetrahedral. All of these atoms mark out the points in space that we call a tetrahedron. But suppose that we had one of them was a lone pair. Like this isn't actually attached to anybody. Let's say that this group of electrons was a lone pair. There's not actually an atom up there. It's just an extra group. It's just a group of electrons. If that's the case, what's left over, the atoms mark out a shape that looks like a pyramid, a triangle-based pyramid. In fact, we call this shape Trigonal Pyramidal. Okay, you can see it here. If we put 3 single bonds on there and 1 lone pair, There we go. Trigonal pyramidal. Okay, from molecules geometry. Trigonal pyramidal is the shape of the molecule. The electrons, there's 4 groups of electrons, so that's tetrahedral. But the molecule doesn't have to be the same as the electrons geometry. The molecular geometry is what shape do the atoms make, and since there aren't any atoms up on here, we don't count that as a part of the molecule shape. This shape, what the atoms make, is a triangle pyramid, trigonal pyramidal. What happens if we had 4 groups of electrons and 2 of them were lone pairs? This shape that we have left over here is what we extremely technical scientists call bent. See? We're looking just at the atoms when we look at molecule shape. These atoms mark out a space that is what V-shaped is what I've heard some snooty people call it V-shaped because they don't like to use the word bent. This is a bent-shaped molecule. It's like a right there. Okay? So this should tell you just enough about VSEPR theory to get you going on your lab and also to help us get a jump start on analyzing the lab once we're done with it.